For this part is Professor Motoi Wada from Doshisha University. So, Professor Motoi Wada is the head of the Plasma Physics Laboratory of the Graduate School of Science and Engineering in Doshisha University. And then, okay, so we have been collaborating, the Department of Physics, especially the Vacuum Coating Laboratory, has been collaborating with Wada-san, as what he likes to be called, for quite some time now. And then, okay, so he, of course, every time that Wada-san visits here in Ateneo, he graciously accepts to give a seminar or talk to the students here in Ateneo. So anyway, without further ado, so here is Professor Motoi Wada, or Wada-san.
Thank you, Christian. The title of my talk is given is from gravitational wave to nuclear fusion, and the art of science and technology too. The two stand for naturally. We have the very first part, and the first part, since I'm a Japanese, and the neutrino physics is merged substantially in Japan. That is because we have the source for producing neutrino, which is my part. I have several former students of mine, working at J-Park Accelerator Facility Complex. I do not know anybody working at chemiocandesite, but in collaboration between the two research institutes, Japan Physics had made first observation of the neutrino oscillation clear. So that had been the first part. The thing I should like you students to comprehend is you are not very far from doing the fundamental physics experiment. Maybe you are learning technology. I also introduced the story of Jack Kilby, who won the Nobel Prize by inventing large-scale integrated circuits. Okay, so you can be practical, you can be fundamental, you can be general, you can be specific. If you love the art of science and technology, then you can take part in this splendidly interesting, exciting business. So let me start. The art of science and technology, part 2. Actually, I cannot see the screen, so I basically watch my PC so that which panel is in front of me. The very first slide I showed you in the previous talk, I do not remember which panel I utilized, but the statement is exactly the same. It's quoted from Paul Andreas Molicius Dirac. What he says was there is a moral to the story, namely that it is more important to have beauty in one's equation than to have them fit experiments. You might disagree, but it is certainly true that Pam Dirac liked or even loved the beauty in mathematical formulation of quantum mechanics. Shinichiro Tomonaga, Japanese physicist, worked on electrodynamic theory, invented the equation, which was not extremely beautiful as the one of Pam Dirac, and Dirac really hates the equation developed by Shinichiro Tomonaga. But you will see how important it is to utilize mathematical language to comprehend our substance, nature. So, excuse me. The picture you have seen on this panel is, maybe you know, this is the first detection of gravitational wave. It has been the real excitement the world over. So everybody was excited. I was excited, of course. They spend a fair amount of time to confirm this is really the signal from gravitational wave. And they checked thoroughly the apparatus, and this is really the part of technology, and they are confirmed about the scale of their calculation. This is physics part. And then this is the real success of the two sides, technology and science. Were it not for enough technology, we couldn't have achieved this observation. So let me start the explanation of the gravitational wave observatory system. Now, from now on, it will be the era of gravitational wave space observation. The facility name is LIGO, Laser Interferometry Gravitational Wave Observatory. So they clearly state that they're gonna observe universe out of gravitational wave. Okay? And the picture you are seeing is a kind of imaginary, half imaginary, half observed. Picture of two black holes collapsing into one with the enormous amount of angular momentum. Maybe you have learned angular momentum. Have you got a good credit in fundamental physics? Angular momentum, conservation of angular momentum is very important, which shall appear later in my talk. So, LIGO facility is the interferometer, gigantic interferometer. You know the name of Michelson-Morley or Mach Zehnder? They are the interferometry. Okay, so if you set up the light source, which used to be sodium lamp, not laser. Okay, sodium discharge lamp produces fairly narrow bandwidth wavelength spectrum. Therefore, you can utilize it as like a laser, not exactly laser. You can stabilize the frequency, thus wavelength of laser, by actively control the resonator. Okay, so the laser beam is now extremely precise, and on the path of laser. The blue one are the support. And the detectors, not exactly detectors, but it's a glass, which is really heavy, is levitated or suspended by these strips. And the laser beam goes through this, and then we have the half mirror here, so the interferometry occurs between these legs before get into the detector. So my explanation might not enough, so I will let the expert.
LIGO stands for the Laser Interferometer Gravitational Wave Observatory.
LIGO is really two observatories that work in unison in tandem. The LIGO interferometer has arms that are about 2.5 miles long, 4 kilometers. We have a laser. The laser produces the purest light you can possibly make. It produces light that's so coherent that it's capable of detecting gravitational waves.
We have these very massive mirrors. They weigh 40 kilograms, which is 88 pounds. They're about this thick, and they're just the purest material you can imagine.
The NSF, of course, had to be the source of funding for anything that would be as expensive as this.
This was going to be a very high-risk experiment. It was from its very inception.
If you think about this in the 70s and 80s, I'm amazed at how bold it was to do this, and visionary. It was bold and visionary. There's no other way to describe it.
NSF management, the National Science Board, they had to really step up to that. And they had a lot of discussions, brought in a lot of experts. There was great debate going on. But in the end, the people who thought it could be done won the day, and they went after it.
Gravitational waves were predicted by Einstein about 100 years ago, and they are dynamical perturbations in the fabric of space-time, ripples in space-time, if you will.
A ripple in the fabric of space and time, the same way as a ripple on a pond is a ripple in the shape of the surface of the water.
Nobody really believed that you could ever detect them because the size of the effect is so small. 1,000th the diameter of a proton.
Even Einstein himself never thought a detection would be possible.
I tried to do this back in the 1960s when I was a student. We couldn't make any progress. We didn't have the technology.
The idea was extremely simple, and it turns out to be the basis of light. What the gravitational wave does, it stretches space this way and compresses space that way. So you exploit that property. Put one object here and another object over there, and let the gravitational wave go through that system, and it'll change the space between these by contracting that one and extending that one. And I came to the conclusion that if you made this long enough, if you didn't make it a little pipsqueak thing like this, but if you made it sort of kilometers scale, you could probably get these extremely precise measurements.
Nobody had ever made something like this before, so there was a lot of technological challenges that needed to be overcome.
The precision that was required it was just amazing, mind-boggling.
The MIT group has typically concentrated on developing new techniques to make the instruments work, and then to work on also data analysis algorithms that are well informed by the understanding of the instrument.
We have observed gravitational waves from two black holes forming a larger black hole.
Two black holes merging together, literally nearly the speed of light, to produce a bigger black hole. How cool is that?
I said, holy mackerel.
This is the beginning of a whole new way of studying the universe.
It's monumental. It's like Galileo using the telescope for the first time.
Every time we have pointed a new instrument into the sky, nature has revealed secrets to us that we haven't known before. And so I feel very confident that this is just the beginning of such an era for gravitational wave observations as well.
Who knows what we'll see?
I would love to see Einstein's face if he could read this article that we just put out. I mean, he would have been as dumbfounded as we are, because it's a wonderful proof that all of this incredible stuff, the strong field gravity, is in his equations. Just imagine that. To me, that's a miracle that that happened. Man's thinking, and also all the elegance, not only in the theory, but the elegance in the experiment. I mean, that is a human endeavor that I think everybody in the world should be proud of. I had to tell you that.
Okay, that's it. So, as you have seen, it's a gigantic monstrosity, okay? And we have two of them. The American North American continent, okay? So, it's really epoch-making. People were not really sure if they have detected the 1,000th of our proton diameter. That's 10 to the minus 18 meter, or 1 atometer. Maybe you haven't recognized that kind of unit exists. Okay, so that's very short distance. Okay, and still they say that they could have measured that. This distance had been created by the warpage of space. Now, you can recognize space in 3 dimensions. After 4 dimensions, you cannot really recognize, okay? Now, Einstein, for some unknown reason, recognized that, okay, we have warpage in some other direction or the other axis, other than x, y, z, or even t. So maybe some of you, maybe a graduate student, could have seen this space-time equation or Einstein equation. So it describes how the gravitational field produces warpage of space. Okay, so according to this, there is a big question about the cosmic term, cosmological constant, which had been introduced by Einstein, which had been challenged by the Einstein by himself, if the introduction of the term is correct or not. But here is the equation. That's very simple. Certainly, it is a tensor equation. So if you if you're not very familiar with the tensor equation, it looks difficult, but it is actually not. You know, it's just the simple addition and multiplication. Maybe the first person. Do you know who he is? Maybe the first person who recognized that as the formula or as the form itself, mathematics is so easily described. What is happening in the physics world is Galileo Galilei, and so Galileo Galilei happened to be the inventor of ordinary telescope. So he designed, fabricated telescope, Galileo type telescope, and he even looked into sun. And later he lost all lights. He got blind. That could have been probably because he looked into his telescope too much. But according to his saying, the book of nature is written in mathematical language, and the symbols are triangle, circle, and other geometrical figures. Okay, so do get into mathematical business, geometry, trigonometry. If you draw the graph, you don't really have to differentiate anything or integrate anything. You can grasp the feeling, what is happening in nature. Once you understand how you describe nature out of mathematics. So, you don't only have to read it. This is the statement by the LIGO that this discovery is really, truly epoch-making. There have been two homeworks for humankind. One is whether we have understood correctly the Einstein's equation. This is the homework from the Einstein. And the other one is the identification of black hole. The black hole movement had been predicted in accordance with the present-day physics. So, like neutrino, there is no real big difference between the neutrino oscillation and the gravitational wave telescope. We have the fundamental principle. We try very hard to prove that the theory is correct out of experiment. But in order to do the experiment, you have to spend awfully a lot of effort. And the effort is this. This is actually the invention by Japanese scientists who used to work at LIGO some 15, 20 years ago. So he worked on this device to cancel the noise. It has been a tremendous effort. As you have recognized, you have to distinguish 1/1000th of the radius of proton. Proton is not an elementary particle anymore. Proton is composed of quarks up and down. But still, it's a very small particle, 10 to the minus 15 meter. Okay. and 1/1000th of the distance of the proton radius is awfully small. So naturally, you have to fight against all noise. If you walk by the side, then you will get a huge noise or signal, okay, whichever. So in order to make this interferometry possible, these optical sensor electromagnetic actuator that cancels the noise was important. So let's go into the practicality. Now, as I mentioned, anybody working in technology is terribly important to prove fundamental physics. Okay, the level of noise is plotted as a function of frequency. Maybe you have heard the name of 1 over f. So the noise goes 1 over f. Now, if you have a radiation of all kinds, we people emit microwave radiation around 10 micrometers. Okay, and seismic wave, a pendulum, and shock noise, thermoelastic, and Brownian motion of our atmosphere. They goes to the square root of hertz type noise. Now, if you take a look at the ordinate, as it is already 10 to the minus 16 here, down to 10 to the minus 21. Okay. If you work on physics, you can recognize. If you are asked this kind of question to ordinary people, what is 10 to the minus 21? They wouldn't recognize, okay? 1/10 of a million, maybe, okay, but not 10 to the minus 21st. The actual measurement is this, okay? Now, again, you take a look at ordinate, 10 to the minus 16, down to 10 to the minus 23, okay? So this is the noise level that they are working on. And the black curve represents the theoretical prediction, and the purple one is the result of the improved noise cancellation unit result. Now, it is not only the United States of America working on gravitational wave observation. We also have Kagra unit in Japan too. This is the Kagra unit is located very close to neutrino detector Super Kamiokande. So we Japanese are kind of mole and should like to dig a tunnel beneath the mountain. So we set up 3 kilometers long interferometer. So it is not exactly 4 kilometers, but we presumed that putting the telescope underneath the ground might help the detection. So the present status of the construction looks like this. So this is underground Kagra gravitational wave telescope. I hope you can see our people standing here. This is the rubber cone, typical rubber cone. So the telescope is embedded underneath the ground. Now, what they are trying to see is a signal from the universe. Now, maybe you have heard the name of Big Bang. And after the Big Bang, we got the inflation. Now, during this stage, as I will come back to it later, you have the background radiation, which is in the microwave range. So we are detecting this microwave from the present, and so we are actually looking back the history, how the universe inflated. Maybe you have heard the name of Hubble constant. The universe is expanded out of Hubble constant. So we have some dark age and the creation of stars, and the old signals are coming from the past to the present. In fact, the signal of our gravitational wave that they have detected is like 1,000 million. Wait a minute. So it's around here. So 1 billion years ago. Okay, So this is a picture of the universe when you place the microwave telescope. Okay, we, as I've told you, the humankind now has a telescope out of gravitational wave. We are currently working on microwave, and we do the experiment also in order to see. This is a kind of difficult job. If we can do that to detect what happened in the origin of the universe. Maybe you have heard that the Big Bang is a quantum mechanical effect. And in the initial stage, we had nothing. Okay, so it's a complete vacuum, right? And then, but you have the uncertainty principle in quantum mechanics. Because of the uncertainty principle, we've got the eruption of energy. That's Big Bang. That's very contradictory. So we've got infinite energy out of vacuum. But people are trying very hard to elevate the present technology of microwave detection in such a way that they can see beyond the Big Bang event. So this is how the universe looked like out of the eyeball of microwave by Wilkinson microwave astronomy facility. So you might assume that universe is isotropic. You should like to assume that everything is isotropic, but that's untrue. So it shows strong anisotropy. And the reason for observing this anisotropy has been debated for many years, and experimental people are working on this. So radio scientists working very hard to elevate their technological level in such a way that we see next to or beyond this Big Bang event. Okay, coming back to some astronomical physics. This is the imaginable picture of our colliding two black holes, which have been detected by the LIGO facility. Now, you may be interested how we come up with black hole. And you have, some of you have heard about the neutrino. The neutrino detection had been first made by the supernova event, okay, the explosion of the supernova. Any planet leads to supernova. So supernova is supposedly the recycler of the cosmology. So you first start with any star like sun. Typical sun-like star will get into the small red dwarf, and then by releasing the outermost gas, then it becomes white dwarf, very close to neutron star, and then further collapse by a gravitational force, and then becomes supernova by hitting certain critical point. Now, if the star is larger, then it can go to directly red giant and go to supernova. So simply explode. The mass is too much. Or blue compact star and then becomes the supernova. So again, as I mentioned, supernova recycles matter. Okay, so you start from hydrogen, then the hydrogen gets to helium. You might know that even iron or some other heavy elements are present inside of the core of solar system. Okay, then the solar system, upon losing the nuclear fusion energy, collapse by gravity, and then all of a sudden it explode, and then convert all nucleus into the original proton and neutrons. Okay, so it's a kind of fascinating recycling process. And then after supernova, if the mass is too much, you'll create black hole and neutron stars. This is the image picture of black hole. Now you cannot see black hole. From this direction, you would observe something really dark. No light comes out. But along the direction of the rotation, you would see the emission of matter again. So black hole, again, is the cosmic recycler. So these things later, from now on, will be clarified by the gravitational wave telescope. But as I have mentioned to you, we already have microwave telescope, which goes back to the age of Big Bang, and we are trying to detect what happened before some earlier stage of Big Bang. We also have Hubble Space Telescope. Now, this thing is up us, right? So it's just the stays in the stationary orbit and constantly taking a picture of the universe. Inside of the Hubble, you have whole plenty of our highly advanced equipment. Well, certainly this has a mirror and lots of cameras, but cameras in all wavelength range. Okay, so you can take the picture out of X-ray, certainly visible range, infrared, again microwave, and nearly all frequencies, not exactly all, but any detectable frequency. So here is one example out of Hubble telescope. So this is the original picture, and by combining these two, human brain can construct what is going on and the formation of the galaxy. Okay. Now, you would imagine the central red part as a galaxy. You are wrong. We have whole plenty of matters around the circulating galaxy. Okay. This has been first detected by the images of Hubble, which is in outer space, extraterrestrial space. Therefore, there will be no signal deterioration due to our water, particularly water vapor is very bad. Water vapor absorbs infrared region, okay, so, and also some are vacuum ultraviolet range because of the existence of proton. So the Hubble telescope clearly says that not only the light in the visible frequency, but also the light in the infrared region. Now, if you take a look at the space out of the kind of eyeball which is sensitive in X-rays and infrared, then the structure of universe is entirely different. Now, I wonder if I can show all the pictures, but I hope you can get some hint about Hubble. is not quite long to see the video through, but I would rather proceed because this particular Hubble telescope is now being utilized out of X-ray imaging, what is going on the surface of our solar system. So not only we are looking at far end of the universe, but also we try to clarify the situation around us. What are the fundamental principles governing the solar system? The reason why I should like to tell you this is because I specialize in plasma physics, and the solar flare movement is governed by plasma physics equation sets. So, okay, this is also the picture by Hubble. Okay.
Solar flares may seem like faraway events, but they can damage satellites and even ground-based technologies and power grids. Every 11 years, as the sun reaches its maximum activity, they become bigger and more common, and that increases the chances that one will significantly affect Earth. So what are these solar eruptions? A solar flare is basically an explosion on the surface of the sun, ranging from minutes to hours in length. Large flares can release enough energy to power the entire United States for 1 million years. Flares happen when the powerful magnetic fields in and around the sun reconnect. They're usually associated with active regions, often seen as sunspots, where the magnetic fields are strongest. Flares are classified according to their strength. The smallest ones are B class, followed by C, M, and X, the largest. Similar to the Richter scale for earthquakes, each letter represents a 10-fold increase in energy output. So an X is 10 times an M and 100 times a C. Within each letter class, there is a finer scale from 1 to 9. C-class flares are too weak to noticeably affect Earth. M-class flares can cause brief radio blackouts at the poles and minor radiation storms that might endanger astronauts. It's the X-class flares that are the real juggernauts. Although X is the last letter, there are flares more than 10 times the power of an X1, so X-class flares can go higher than 9. The most powerful flare on record was in 2003, during the last solar maximum. It was so powerful that it overloaded the sensors measuring it.
Okay, so this is a picture I should like to show. Do you know the diameter of sun? 1 million kilometers. Okay, you cannot even imagine. Okay, and look at the size of this plasma guy, solar flare. It's enormously large. Okay, and naturally, that particular thing can radiate proton beams. This is radioactive. Okay, so you have seen it in certain part of the world. You can see aurora borealis, and that's nice. But during the time you see aurora borealis, you are irradiated by the cosmic nuclear radiation. So that is what is happening, and that can be understood out of the observation. Okay, and that Hubble Space Telescope, you understand, is launched by I think it's a space shuttle. Okay, the space shuttle launched the Hubble telescope, maintained in the extraterrestrial space, and put into the stationary orbit. You know, this is really technology. And the technology is quite necessary to understand the plasma physics there. You have seen that the magnetic field is formed, and the electrons are stuck around the magnetic field lines, and on the other hand, the high energy proton beams try to escape out of the solar flare, causing the nuclear radiation down to the globe, Earth. So there are. You might think that there are two aspects. One is fundamental science, and the other is highly advanced technology. And you might think that they're separable, but in fact, it's inseparable. Okay? So without the advancement of technology, we humankind cannot go any further in fundamental physics. without any fundamental physics, people not motivated to cultivate in next dimension state-of-the-art technology. All right, before getting into the finishing part, I should like to come back to the nuclear fusion reaction occurring in the solar system. You start from two protons. Two protons get together to form one deuteron. Now, one deuteron with another proton can form three helium. It's not alpha particle. It's missing one neutron. And then these two, three helium get together to form alpha particle. And then this chain reaction continues in some solar system to produce continuous energy. Now, we humankind, why so stupid, I don't know, try to bring this solar reaction down to the Earth. So our proposal is just to make a reaction out of deuteron and triton, which is another isotope of hydrogen. Now if they get together, it produces enormous amount of energy again. So this nuclear fusion reaction can be the next generation energy source. But again, as you can think about the collision between the charged particle should circumvent the Coulomb potential barrier. So you need to agitate, or you need to energize the constituent particles. So as you have seen, the solar system is a gigantic plasma. But if you come down on the Earth's surface, then you have solid, liquid, and gas, and plasma you really observe. So, we humankind have studied plasma physics to realize nuclear fusion reaction, the nuclear reaction which is happening in the solar system. Now the question is, how can you hold sun on the Earth's surface? The temperature is awfully high, therefore you have to think about a good way to confine, if you want to say it that way, the plasma. But certainly they can rupture like a balloon, so we should like to utilize the electromagnetic wave because we cannot utilize the gravitation. But on the other hand, you can also compress the plasma out of radiation pressure by laser. Again, humankind has another good way to induce pressure by electromagnetic radiation, that's laser. For your student, I can recommend several textbooks, An Introduction to Controlled Thermonuclear Fusion, where you can find some graphs, like the mass defect per nucleon, which is very high in the uranium and also very high in hydrogen. And helium is, the reaction from hydrogen to helium causes the maximum mass defect, which can be release of energy by the nuclear reaction. So as you might know, speed of light is 2.998 times 10 to the, I'm sorry. It says -8, no, +8. And Einstein's relation is delta E is m times c squared, so the energy you produce is enormous. Now, if you want to realize nuclear fusion for DT reaction or deuteron-deuteron reaction that you have seen in the solar system, you have to cope with the effect of radiation. Bremsstrahlung, anything gets hot, radiates. Okay, so for humankind, it's infrared region, If your electric stove is well hot enough, then you see red color, right? So that's rich in red infrared radiation. These radiation are called Bremsstrahlung. This is German. So brake radiation. Okay. Strahlung is radiation. Brems is brake. Because of this effect, you have to be extremely careful of controlling the temperature and the content inside of the plasma. Now, hydrogen at higher temperature, fully ionized, that's the situation of sun. Okay. Now, if hydrogen doesn't have any extra electron on the closed orbit, then it doesn't radiate really much. But on the other hand, if you put in, like, for example, tungsten is very heavy, or maybe iron is also heavy, not awfully heavy as tungsten, then they can capture electrons at the outer shell, okay? Then it radiate enormous amount of energy. So you are not supposed to get any impurity in to your plasma. So the plasma confinement becomes extremely difficult, and we scientists working on the plasma seriously tackling with this problem, as I mentioned previously, out of laser and magnetic field. Now, as I'm working on magnetic confinement of plasma, I will briefly describe what kind of structure do we expect for the future nuclear fusion reactor. This is out of the textbook again. So we confine deuterium, tritium, 50% mixtured plasma and the core, and then you have to absorb heat. So the walls surrounding this reactor is 900 Kelvin. That's very high in temperature. So you have to prepare a proper material. It used to be carbon as the candidate material. Now, some people say this is crazy, but we are going on to tungsten because the melting point of tungsten exceeds 3,000 Kelvin. We are not quite sure if this choice is right or not, but we are going to do the experiment out of ITA facility, which I will explain to you immediately. Now, in order to confine this plasma, now in case of sun, you have strong gravity, therefore you don't need anything. But on the other hand, if you want to keep this plasma on Earth's surface, you need strong magnetic field, which will act as if you have some gravitational field. So, naturally, we go into the superconductor business. So if you take a look at the temperature of the outermost shell, it says 4 Kelvin. Okay? You may call it stupid. So starting from 900 Kelvin, with only several meters away, you have 4 Kelvin temperature in order to sustain a superconductor. But this is what we are doing, like to the previous case of gravitational wave observation of the universe. You see, we detect 1,000th part of proton radius, okay? And we just shield the temperature of 900 from 4 Kelvin with only several meters. Okay? That part is the combination of physics and technology. Now, it's extremely difficult to control plasma. The plasma is very high temperature, and as you have seen in the case of solar flare, the plasma can generate magnetic field. You understand? We try to stabilize the plasma inside of the magnetic field. We should like to confine that. But that particular plasma can generate magnetic field by itself if they commit nuclear fusion. Okay? You have already energy there. Magnetic field, in a sense, is regarded as the energy field. If you are store enough amount of energy in the field, then it can generate magnetic field, or both electromagnetic, but magnetic field. Then the magnetic field will disturb, that produced magnetic field will disturb the confinement magnetic field. So you need a whole plenty of control. And so is the nuclear particles. So in the toroidal reactor core, we commit nuclear reaction in lithium, beryllium, and the fuel hydrogen isotopes are put into the system. And you have to remove heat, and also you can recover tritium. So once you start the nuclear fusion, it's like the uranium-based nuclear fission reactor. You gain the fuel. Okay, so you put in deuterium and tritium, and then you gain tritium. Deuterium can be recovered from seawater. Okay, and you can just constantly feed deuterium into the system, and then you get additional tritium. So you have more fuel by running the nuclear fusion reaction. So naturally, this is very charming, impressive scheme for humankind to get energy, okay, obtain energy. So there are so many proposals to make this effective in the past. Not anymore. We have only 2 schemes to sustain continuous nuclear fusion reaction. The straight magnetic field can confine the charged particles, but again, if the particle hits the wall, then you lose them. Therefore, some clever scientists come up with the idea of utilizing the magnetic field, as I mentioned, in such a way that toward the end, the magnetic field gets stronger to generate more magnetic pressure. But again, you have the end. So collisional process, maybe some of you might have already learned about the phase space. There is phase space instability. So if you have any isotropy, your system gets unstable. So some brilliant guy come up with the idea of donut-shaped plasma. This is out of my textbook. So I let my students work on drift motion of the particles, upon which you can predict how well you can confine the plasma inside of the specific magnetic field. You can compute out of our field calculation software. The field is very complicated. Okay, just the ordinary toroidal or donut-shaped magnetic field won't confine plasma well. It's really known. Therefore, we couple toroidal and the component, the particle to toroidal magnetic field, which we call poloidal. Yes, poloidal. And then the particle magnetic field. Do not try to remember, okay? If you are enrolled in this business, then you remember naturally. So as for the time being, just imagine that there are some jargons about the magnetic field structure of the magnetic fusion reactors. Okay. The principal candidate is tokamak. Now, in tokamak device, we introduce current in the plasma. So we have learned a lot from solar flare. Now, solar flare generates magnetic field, and it produces the filament of plasma. Now, this particular plasma filament carries current. So there is the effect called pinching effect. So you just let the current flow through, then you generate the magnetic field. This particular magnetic field can confine plasma with the magnetic pressure. So the Russian scientist, Karamtsev, invented tokamak device by injecting the current into the torus. Now, how does it look in recent years? This is the picture out of jet facility. Okay, joint European torus. which has been shut down for quite a while. So as I mentioned, any place which is high temperature and hydrogen plasma do not produce any radiation. You see the total empty space. And that part, we have a very high temperature. Now the bright side, or the glowing part, contains fair amount of bound electrons. Okay? So therefore it radiates the visible light. So the temperature there is far much lower than the central part. The central part is 10 kilovolt. Well, 10 kilovolt is 10,000, yes, electron volt. So 10,000 electron volts, 100 million Kelvin. Okay, so the device is now already fairly gigantic. You can see our the worker working in the torus, and if you ignite the plasma, only the lower part radiates the light. So, ITER project again. The picture from the Hubble Space Telescope is utilized for the ITER project homepage. Just the brief introduction, what we are doing. This video had been prepared by French team, so it's stationed there in France.
The sun, like the stars, draws its energy from the fusion of hydrogen atoms. This nuclear reaction is 1 million times more energetic than the strongest of all chemical reactions. Since the early 1950s, scientists have been drawn to this powerful energy source and have sought to recreate it on Earth. The stakes are enormous. Fusion could provide a source of large-scale energy, one that is safe, available anywhere on Earth, in unlimited quantity, and with no negative impact on the environment. The fusion adventure began in the 1950s with a young Russian soldier called Oleg Lavrentiev, who first proposed the idea of a fusion machine based on the thermal insulation of high-temperature plasma using a high-voltage electric field. In the following years, many fusion machines were built and tested in the Soviet Union, the United States, Europe, and Japan. These initiatives were triggered by the first major oil crisis. The hunt for a new energy source had begun, both in the public and the private sectors. Despite the progress, it soon became clear that when it comes to fusion, size matters. A bigger machine was needed. Through the ITER project, 6 nations, China, India, Korea, Japan, Russia, the United States of America, and the European Union have agreed to pool their financial and scientific resources to prove the viability of fusion as an energy source. ITER is the Latin word for the way. Its goal is to pave the way to fusion power. From 50 megawatts of input heating power, ITER will produce 500 megawatts of thermal power for at least 300 seconds, the first fusion machine to produce net energy. The chosen site was in southern France. And so, here we are today, building the largest fusion machine ever. ITER is based on the tokamak concept of magnetic confinement. First, the fusion fuel, puffs of deuterium and tritium, is injected into a vacuum vessel. Then a powerful magnet, centered in the core of the machine, is turned on, inducing a current across the gaseous mixture. The voltage rips electrons from the atoms, forming a particle soup called plasma. Now the superconducting poloidal and toroidal coils are ramped up, locking the plasma inside the vacuum vessel. Squeezed together, it quickly heats up to 10 million degrees centigrade, but that is not good enough yet. To make the particles fuse, the temperature needs to be increased further. Radio and microwaves are fired into the plasma together with high-energy beams of deuterium atoms. until the plasma reaches 150 million degrees. Hot enough, highly energetic neutrons. While the helium particle remains in the plasma, helping to keep it hot, the neutrons escape the magnetic confinement and hit the surrounding metal wall. Once they have slowed down, the neutrons release their energy by emitting heat, which is finally turned into electricity. While work progresses in southern France, manufacturing begins in ITER member factories all over the world. Instead of providing the monetary value of each system or component of the ITER machine, the member states will deliver the completed components to the ITER site, where they will be assembled in what is certainly one of the most complex jigsaw puzzles ever conceived. The largest components will arrive by sea and be unloaded near Marseille. From there, they will travel to ITER along the 100-kilometre ITER itinerary, which has been especially adapted by France to receive the exceptional size and weight of the loads. The delivery of the first completed components is scheduled for 2014. From that moment on, approximately 6 years will be necessary to complete the assembly, testing and commissioning of the machinery. Back at the construction site, mighty bulldozers and towering cranes dominate the scene. Just a few years from now, ITER will tell us if the dream of a limitless energy source can finally become reality. The 35 nations united under the ITER flag believe that fusion is the future. And so do we.
Okay, so that's the present status. So you have seen that the actual machine is under construction. I have to tell you the truth that the construction is ongoing and the machine will be ready, but the components and some countries like France, Germany too, they run out of research money and some part are not coming in. Japan and Russia are putting in their component as scheduled, but not other countries. So we have big anticipation of whether we can fire the plasma while I'm alive. But well, this is a real serious problem. So we are constructing this. Maybe you can see typical 2-meter men, gigantic monstrosity. Approximately 40-45 meters high. Very big experimental facility like LIGO. Okay. So this one is for energy production. So I have another pictures. How long am I supposed to speak? Maybe.
Well, the whole event is 1 hour and 30 minutes, so we can. I think we still have about 5 minutes. Now.
Okay. Okay, I've got 5 minutes. So we actually put in the deuterium beam. So we make the artificial nuclear radiation like we are doing for the neutrino measurement. And here is a pretty big beam launcher, which is smaller in energy but rich in flux. So the total amount of power is enormous. We also utilize the fundamental principle of you to heat up your bread in the morning, microwave oven. Okay. By utilizing the microwave oven, you can heat up the plasma too. And with those two, what we call the heating, plasma heating devices, we established plasmas. This is a picture of the one you have in National Institute for Fusion Science. If you come to my place at Doshisha University, I will be really much delighted to take you to this facility, which is located in the Gifu area. Now, on the other hand, I myself doing the neutral beam injector business, and this is the picture that we have the collaboration with the Japan Atomic Energy Research Organization. But again, if you see these pictures, you would believe that, okay, that's really distant from me, this is none of my business. But you student can participate in any kind of this project. This is the one which was completely designed by one of my students, and we are running the oxygen plasma, so it's yellow, greenish in color, but if you run the hydrogen plasma, it is bluish in color. This is, the artwork of my students, right? So they are, one of my students had started, and the second one succeeded at the magnetic confinement, and the third one worked on the measurement of negative hydrogen ion inside of the machine, and the other one put in oxygen to see the performance as the confinement device for negative ions. So it's a series of work of my students. So you can do this kind of experiment here in Ateneo, okay, under supervision of your professors. This is another example of how you can make the plasma devices practical. This is also the design of one of my students. Okay, so you can learn Japanese industrial standard and then make some drawing, ask the shop people to fabricate your device and put in gas. I took the picture with the hydrogen gas cylinder. Okay, put in the gas, hook up the turbo pump, evacuate, apply high voltage, then you have plasma. That particular plasma is not very far from the plasma we are confining in ITA. So, in conclusion, I hope you have seen the very nice pictures of LIGO and ITA and Hubble Space Telescope. But you're not really far from here, distant from there. Maybe you cannot go directly to LIGO or ITA. Well, certainly, if you come to Japan and take some credit, certainly you can graduate from Ateneo, and if you go to a National Institute for Fusion Science in Japan, then you can actually visit ITA as a scientist. Okay? You can visit Kagra, you can come to NIFS, National Institute for Fusion Science, you can come to Doshisha. You can work here to do the research in plasma science too. The most important thing of all is keep your motivation. You can find the proper topic. You have your own talent that you can believe in. Okay, so trust yourself. You can cultivate your talent by learning properly. Your curiosity is the best asset that you have. Just please come and join us. Okay, I'm just a stupid scientist. Okay, just curious in nuclear reaction, what is going on in space science. But it is very fun to work and stay in physics. Okay, that's it.
Okay, thank you very much, Wada-san, for your very inspiring lecture. So we have about a couple of minutes of question and answer. So okay, so if you want to ask a question, you can come here in front and then ask your question through this microphone. So, any questions? Okay, to start the yeah.
What can you say about the ether theory? Ether, yes. So,
Yeah.
maybe they look like a whirlpool of ether, also the gravitational field they're measuring.
Okay. Ether theory is in principle denied. That's a very long time ago. The Michelson Morley had done the experiment very similar to LIGO. Okay. Now, if you have the constant interferometry signal out of LIGO, then we have to come back to ether theory too. Yes. But as for the time being, we're not aware of any stationary ether signal. So again, as for the time being, we have to deny ether, the presence of ether. But it's coming from the other part. I happen to address Shinichiro Tomonaga. Okay, anything you do the computation out of quantum mechanics, maybe you know. You should. I think you know. But if you go into the quantum mechanical system, then every integration diverges toward the end. You introduce new parameter, to correct the effect, observed effect. So this is the reason why Pam Dirac said that. Okay, fit into the experiment doesn't mean anything. But we have to, work half experiment, half theory. Okay. The theory, we certainly look for more beautiful theory, like Einstein's equation. Einstein's equation looks very nice, and Einstein hate the cosmological term because it doesn't look nice. Okay. So it's a kind of trade-off between the experiment and fundamental theory. Now, as for the time being, the fundamental theory can hold without including the ether. In the old days, they cannot really think about the warpage of space. They are hesitant to introduce another dimension. They stayed on the fourth dimension. Now we have 12, maybe. So superstring theory needs 12-dimension calculus. So we human beings come to that level, and even at another point, I think we don't really have to introduce ether. Okay, that's my understanding. Maybe not everybody's. Yes.
In the ITER project, there was a slide where
Yes.
you had an input power of 50 megawatts,
Yes.
and the output would be 500 megawatts
Yes.
of a different type of energy. How does this not violate the conservation of energy?
Oh, this is because of nuclear fusion reaction. So 50 megawatt is the energy to create the temperature of solar system. Okay. Well, in case of nuclear fission reaction, it's quite easy. Maybe you have heard the name of Fermi pile. Fermi pile is composed of carbon and radioactive material. So if you just pile up, then above certain limit, it gets heat and produce the controlled fission chain reaction. Okay, so you do not have to put in any power. But on the other hand, that particular chain reaction can hold only at the elevated temperature, which is far away from the Earth's surface temperature. So we live in 300 Kelvin, but the environment for fusion reaction to hold in a sustainable mode is, as I mentioned, at least 1 million Kelvin. So in order to elevate the temperature, you need energy. This is 50 megawatts. But after that, you have 500 megawatts of energy, which is coming out to the heat absorption part. Now that particular heat absorption will be converted to electrical energy, and the 50 megawatt will be returned back to the heating energy. So this is the reason why the steady state nuclear fusion reactor lives with only the energy supply. Okay, so it certainly produces energy, but in order to maintain some temperature, it requires input energy. But that if you war on that particular input energy, then you can sustain the temperature. Therefore, at that sustained temperature, you have the nuclear fusion chain reaction, which generates 10 times more energy than you input.
I have another question regarding the practical and social implications
Yes.
of this new energy source.
Yes.
Will there ever come a time where you would have free energy for everyone in the world? If you generate 10 times more based on your input, could you
Yes.
just give away this energy?
Well, I'm not sure. Okay, for their first 10, 20 years, they have to, this is just investment. Humankinds are spending enormous amount of money to get new energy source. So they have to recover the investment. Okay, so maybe you might as well ask the professors in economics department. I'm just a humble scientist, not earning much. Okay? I'm not really shooting for making money. Everybody knows that I don't know much. So it's like the life in the university professors in the Philippines. We don't know much. Okay.
I think we have time for about 2 more questions.
2 more questions.
Any questions from the students? Anything?
Yeah.
How can students from Ateneo go to your lab? Do they need to do work collaboration with Dr. Mahinay? How do they go into that field, into the...
If the student is interested, okay, I know Ivan Klaba, Christian Mahinay, anybody, maybe through you. You already have my name card, right? So, if Mombusho Scala is available. And also, Christian and I are working for some short-term visit program, like the one sponsored by the DOST sandwich program. And come to my laboratory, take a look at the National Institute for Fusion Science, look at the LHD, or maybe if time allows, I can take you to our Spring 8 device J-Park facility. That's possible. So yes, maybe you can ask Christian, Ivan, you professors in physics department. Any scheme, you can talk to me. Yeah.
So one more question.
Yes, one.
The ITER project is massive and involves many nations. So, did you do a scaled down model first, or did you propose it?
Okay, we have finished the scale down model already. So what we have figured out is only 2 schemes are possible. With regard to magnetic fusion, in case of laser-driven fusion, they are actually going into the opposite direction. Okay, one single gamma can produce positron and electron. Okay, so they are trying to create matters out of intense laser. Okay, so they are shooting for another Nobel Prize. The pair production process out of gamma is a known process, so that's not very exciting, but they are going to shoot to produce even hadrons, particles based upon quark. Okay, so heavy particles, not electrons. Okay, electrons are leptons, light particles, and the laser fusion people are going in that direction by producing very, very intense laser beam, well collimated, well focused down to a tiny little spot to produce matter. Okay, so out of matter, out of light, it doesn't have any mass. They want to produce matter with mass. So Higgs boson should be present. So that's the direction of the laser fusion group, and we used to work from 1950s, before, before I was born. They make many small confinement devices, they call. The aspirator and the LHZ, helical device, those do not carry current inside of the plasma. Okay, they are well enough stabilize the plasma. Now, it is not the it is not only Japan, but also the Germany or German project to make the sizable plasma good for fusion reaction. Okay, so we are still doing some fundamental exercise type experiment for a fusion, both in Japan, Russia, and also Germany, as I mentioned. So there are three. In the stellarator type confinement, but most of the people believe that tokamak is going to be the final answer to the nuclear fusion reaction. So if you say that downscale experiment, then it's less common at the present moment. In the past, we had many systems like our advanced mirror machine and the Zeta pinch machines, national ignition facilities, which is shutting down very recently, which is in the United States of America. Okay. Now, if you talk about downsizing the nuclear fusion reactor, you are talking. Okay, the current ITER system is too large, too massive, too gigantic. It's 40-meter monster. Okay, so everybody should like to reduce the size. It is true. So if you come up with some brilliant idea of commercial nuclear reactor with a size substantially smaller than ITER, then you can be wealthy. But in order to do that, you have to clarify the physics of the next level.
I have one more question.
Oh, okay.
Since nobody else is asking,
This last question. Okay, so when you showed us the ITER project and the shape of how to make a nuclear fusion device,
Yes.
so it's basically a donut shape.
Mm.
So this is, from what I understand, so this is the shape so that the plasma is self-confining.
Yes.
Right. So so if this is the best shape that we have come up to make a nuclear fusion device, so why do we not see something like this in the stars, for example, in interstellar bodies, donut-shaped stars
Oh, okay, yeah.
creating their own nuclear fusion reaction?
All right. For one thing, we should like to confine the system. Okay. Now, it is more common to see the twin stars or triple stars in the same orbit. Okay. Not exactly the same orbit, but they just are joined together. So as you have seen, it's just the gas cloud. They start from gas cloud, then they condensate. Okay. Then you should ask yourself, how come only one? Right? So it is more common to observe twin. Okay. So that's part of the reason why we see twin of black hole. Circulating, conserving the angular momentum, and then collapse. Okay. Finally, it gets into one spherical symmetry. But at the start, it's toroidal shape, okay? And then they just come into the condensation, so 6 stars, and then 3, then 2, and finally 1. So it's not surprising that humankind had chosen toroidal shape for the plasma confinement or cosmic confinement.
That's all the time that we have for now. So one big hand of applause for thank you very much. Okay. So thank you very much for your talk. So.